So welcome, we're continuing our conversation of sequences and series. And so we've talked about arithmetic. And so just to review those, so if I'm thinking sequence, we have something here that is plus 5, plus 5, plus 5, and so on, 2, 7, 11, 16. And so it's infinite if I include this plot, this comma, dot, dot, dot. So it's an ordered list. If I say what is a sub 3, we should say 11. But what we're going to look at today is something that's called geometric. Geometric. It's really just a different pattern. So if I would have something that is 2, comma, 6, comma, 18, comma, 54, comma, dot, 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 and I'd ask what's the pattern, hopefully you'd look at this and go, oh, times 3, times 3, times 3. And so this is really what geometric is about. We say a common ratio, and that's similar to that common difference. Remember, for common difference, we'd take a term and we'd subtract the one that came before it. So for the common ratio, we're going to take a term. So if I think about the 18, and I divide the term that came before it, 6, that answers 3. It's common because I could take any term and divide the term that came before it. 54 divided by 18 is 3. 6 divided by 2 is 3. So our common ratio here is 3. So really when I'm saying 2 times 3 is 6, times 3 is 18, times 3 is 54, I'm really saying 2 times r times r times r, because that's what we're going to refer to here as the common ratio. Okay? And really that means that we can come up with some equations that are very like the ones we were doing. Like before, we were figuring out, okay, how many steps, right? If I'm starting at 2 and I'm trying to get to 18, that would be 2 multiplications by r. I need to get to 6 and then I need to get to 18. So if I'm trying to get to the third term, a sub 3, I'm going to take the first term and I'm going to multiply by r twice, so r squared. So a sub 3 equals a sub 1 times r squared. And so if I wanted to get to the 10th term, well, wouldn't I start at the first term? I'm going to multiply by r again, again, again until I get to that term, but in this case, I'm going to multiply 9 times. I could even say something like this, that a sub 37 is equal a sub 32 times r to some power. So think about that for a minute. If I'm on the 32nd term, if I'm on pad 32 and I'm trying to get to pad 37, how many times, how many steps do I have to take of times r? Times r. And if you look, hopefully you've seen the pattern that you can just take those numbers and subtract them. So that would be r to the 5th. Okay, which kind of leads us to a general formula. If I want to get to the nth term of something that is geometric, if I start the first term, I'm going to multiply by r n minus 1 times. So here's our formula, a sub n equals a sub 1 times r to the n minus 1. So if I would say something like, here's my pattern, so I'm going to say, let's do another one. So if I'd say, let's start something better. So 64, comma, 32, comma, 16, comma, 8, comma, 4, comma, 2, comma, 1, comma, a half, comma, a quarter, comma, dot, dot, dot. So when you're looking at this, you probably would say that I'm dividing by 2. I hope you're all thinking that. Divide by 2, divide by 2, divide by 2. But if I ask you what's r, r is the thing I am multiplying by. So to go from 64 to 32, so r would be a half. So if I wanted to figure out, like, what the sixth number in the list. So I can even look here and count it off, and I can see that that answer is supposed to be 2. But if I think about my formula, it would say the sixth term in my list should be the first term in my list times a half to the 5th power. So the first term is 64, so I have a sub 6 is 64 times a half to the 5th. You can take your calculator and put that in, but that's 1/32. 1 over 32 is a half to the 5th. So then I have 64 times 1/32, which is 2, which it is in our list. Okay. So that's the geometric series. Now, when you look at this, this is actually something we've done before. Like, so when I think about A equals P times 1 plus R to the T, do you notice that that formula for compound interest is geometric? You know, so if I invest $100 and I say A equals 100, and I say R is 5%, so remember that's the decimal, so I'd say 1.05 to the T. And I say how much is it worth in 5 years or 10 years or 30 years, we would just change this exponent. But really what you're doing is you're multiplying by an additional 1.05 again, which is exactly what geometric is all about, multiplying by an additional value again. Okay, so just making that connection that that compound interest stuff is a geometric pattern. It's a multiplication pattern, and we've seen that, but I'm just showing that here. Next, when we think about the series, so if I would write something like this, let's do 1 plus a half plus a quarter plus an eighth plus a 16th. And what if I want to know what that sum is? And you might say, well, just add it up. And that's true. If there's only a few numbers, you could just add it up. But actually, let me change this. I'm going to come back to this one in a minute, because what I'm going to want to do is think a little bit more flexibly, but let's avoid the fractions for just a minute. So let me do this one. So what if I'd say 2 plus 4 plus 8 plus 16 plus 32 plus ... Okay. Now, there is a formula to figure out the sum. It's like, so suppose I'm wanting to find again the sum. Sorry about the edit there, but so 2 plus 4 plus 8 plus 16 plus 32. And so let me give the formula, and then we'll show that it's giving us the answer that we're expecting. We can talk a little bit about where it came from. But so it's going to be the first term, so A1, so the sum S sub 5 equals A sub 1 times 1 minus R to the n. So A1 times the quantity 1 minus R to the n, and just that R is being raised to the n power, all over 1 minus R. So we can see the sum of these first 5 terms here. So we get 14 plus 16, 30. So this sum is supposed to be 62. So let's see if we can get this, if this formula is working. So it would say the first term is 2 times 1 minus R, again, which is 2. That's a coincidence that A1 and R are 2. That's just the one I picked. And to the n power. So n is whichever, how many things here we're adding, really, because it's the sum of the first 5 terms. So n is going to correspond to that subscript. So 2 to the 5th, all over 1 minus 2. And so if we simplify that, we get 2 times the quantity, 1 minus, so 2 to the 5th is 32. And it's over -1. Don't let that bother you, because there's 2 negatives here. And so we get negative 60, so this is 31. Here, my kitty's joining us, so this is 6. Sorry, so this is a minus 31 times 2 is a negative 62 over negative 1. And so there's our answer of 62, which we already knew. So again, so here's the general formula, S sub n, the sum, if it's geometric, will be the first term, a1, times 1 minus r to the n, again, just that r is being raised to the power over 1 minus r. Now really where this is coming from is recognizing a pattern, and you might have noticed it here that there's a pattern that if I'm looking for this fifth term, I don't know if you caught it, but you end up kind of using that number in it. And then there's a connection back to like it's like this first term, this, let me say it this way, this next term we didn't write down would have been comma 64. And there's a connection back to this first term and how much it's off by. So I don't know if I want to go more into that, but so there's the sum of n terms, okay, if it's geometric. The proof is kind of interesting, but maybe we'll do that in class. But I hope that that's enough to get you started here. And there's one more piece, and that's talking about what if it was infinite. Now we said this, I think I said this, when we're talking about the arithmetic ones, that if I would say 3 plus 5 plus 7 plus 9 plus ... forever and ever and ever until the end of time, and ask you what that equals, we can only say infinity, right? It just grows, it gets bigger and bigger and bigger and bigger, never is going to stop adding. And so when we think about geometric things, that is true sometimes. And that is something that might bother some of you as we look at this. But so here's an example of one that is also infinity. So the one we just did, 2 plus 4 plus 8 plus 16 plus 32 plus ... forever and ever and ever until the end of time, that answer is infinity. Again, it just grows. It gets bigger and bigger and bigger and bigger. But they don't have to geometrically. So the one here that I want to look at is the one that I'd first written down there on the other, up here above. This 1 plus a half plus a quarter plus an eighth plus ... What would that equal forever and ever and ever until the end of time? Now, you might be tempted to say infinity because you keep adding something. And that's true, but the thing you're adding is getting very small. And it's actually getting small quickly. And that's actually important as well when we talk about this language of convergence. But let's think about what r here is. So r would be a half. So if I look at my formula that I just wrote down, S sub n, a1, the quantity 1 minus r to the n, where only the n is affecting the r over 1 minus r. Look at this r to the n. Now, what if I'm saying n is approaching infinity? Okay, so in calculus language, I would write the limit as n goes to infinity. Here we just might write s sub infinity, thinking it just grows bigger, bigger, bigger. So really what that's saying is this is saying a half to a power, and that power keeps getting bigger and bigger and bigger, and I want to know what the answer is. Well, if I keep taking half of a number again and again and again and again, and half, take half, times a half, times a half, times a half, really the only thing that makes sense for me to call that number is 0. So that leads to this formula. If it's infinite, if n is going to infinity, and r to the n gets close to 0, the sum of our infinite series that's geometric will be the first term divided by 1 minus r. a1 over 1 minus r. Why is that? Because if r to the n gets closer to 0, then what that's going to then say is that this whole piece is 0. So the r to the n is 0, so you get 1 minus 0, what's that? 1. What's 1 times a1? a1. Now, just to show that, like here's that series 1 plus a half plus a quarter plus an eighth plus dot dot dot, forever and ever and ever until the end of time. And what does that then equal? Well, the first term is 1. R is a half, so that would say 1 over 1 minus a half, which is 1 over a half, which is 2. Right? You multiply by the reciprocal. So the sum of that is a number. It's actually 2. And so before I get too far, let's make a note here next to this formula for this s sub infinity is equal to a1 over 1 minus r. Let's say that's true as long as r is between -1 and 1. And the reason that restriction is there is because of this statement, r to the n approaches 0. So the only way I can get close to 0 is if r, if I keep multiplying by r again and again and again, if it's less than 1. Think about even if I would take a number like 0.98. So if I keep taking 98% of a number, so think of 1, I'm going to take 98% of it, 0.98, I'm going to take 98% of that, and then 98% of that, again, 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 again. Like that gets smaller. If my number is bigger than 1, it gets bigger. So bigger is a problem because that would be like this scenario of this 2 plus 4 plus 8 plus 16 plus 32 dot dot dot, and that's going to be infinity. Okay, so just on a side note, some of you might be really bothered by this 1 plus a half plus a quarter and just think, how do these plus dot dot dots not end up being just infinity as this answer? Here's a picture to help. So here's a box that is 1 by 2. If I cut this box in half, I don't change the area, right? I didn't lose anything. I still have, it's a 1 and a 1, so the total area is 2. So the original box has an area of 2, and if I divide it into more boxes, its area is still 2. So what if I took this second box over here and I cut it in half? And so now I have a box that is 1 by 1, and a box that is 1 by a half, and another box below it that's 1 by a half. And my area here is still 2. But what if I took one of those boxes and I cut them in half? So there's a quarter and a quarter. And then what if I took one of those and cut it in half? So that's an eighth, and the other side would be an eighth. And then what if I took that and cut it in half, and cut it in half, and cut it in half, and so on until the end of time? What is the sum of the area of all of those boxes? Well, it has to be 2, because that's the limiting factor of this rectangle that we're fitting in. So it's true, it works, it gives us the answer we want. Now, on a side note, it also is going to create something you probably also don't like. So here's what I mean. If I would say this, 0.9 plus 0.09 plus 0.009 plus 0.0009 plus ... Forever and ever and ever until the end of time. Is it geometric? Yes. Times, times, times. What am I multiplying by? Take your calculator if you're not sure and divide two terms. I'm waiting. Do that. And hopefully you're seeing it's 0.1, 1/10. So it's less than 1. It's between -1 and 1. So that means my sum works. My sum should be my first term, a1, over 1 minus 0.1, which is 0.9 over 0.9, which is 1. And this is a fact of numbers that bothers people, though it shouldn't. If we look at this original number, and I wrote it differently, 0.9, I'm going to write it vertically, 0.09, 0.009, 0.0009, and I say forever and ever and ever, I'm going to add these up. Do you notice the number we have is 0.999 ... In other words, 0.9 repeating, which means, so this is true, 0.9 repeating is another way to write the number 1. It's perfectly valid to say this, 3 minus 2 equals 0.9 repeating. Now, some of you are looking at that and you're going, what? This doesn't make any sense. Well, what other number would it make sense to call 0.9 repeating? So if I would say this, like there would have to be a number in between. Like if I think about the number line, and I think about 0.9 repeating and 1, if they're not the same number, there is some number or numbers in between them, right? So if 0.9 repeating is not the same number as 1, then I would have to be able to add something to it to get the number 1. If they're not the same number, obviously adding something to it would give me the same number. So if I wrote out 0.99999 ... and I want to add something to it to get the number 1, the question is, what would I have to add? Well, 0.0, I couldn't put a 1 there because that would be a little bit bigger than 1. 0. Well, every time there's a 9, I have to put a 0. Now, if my list of 9s ever stopped, then I could put a 1 there. But there's always another 9 to look to in the next digit, which means there's always another 0. So if I did that forever and ever and ever, what number did I write down? I wrote down 0. So 0.9 repeating plus 0 is 1. So that's a fact of numbers, and you may not like it, but that doesn't mean it's not true. And it really comes from this idea of geometric. So that should be enough to get you through the homework for 11.3, MyMathLab. And so start that and have a good rest of your day.